Hello everybody, welcome to the course of Solid State Electronic Devices. Today we will be discussing the module number 7, that is Field Effect Transistor, very commonly known as FET. The topics which we will be looking after are the basics of field effect transistors, that is FET, the representation of FET, MOSFETs, functionality of NMOS and PMOS, IV characteristics of the MOS transistor, and the mode of operation of MOSFET. Field effect transistor, that is FET, is a three-terminal majority charge carrier device, the three terminals being the source, gate and drain. It operates as a conducting semiconductor channel with two ohmic contacts. These ohmic contacts are nothing but the source and drain. The majority charge carriers flow from source to drain, whereas the gate controls the number of the charge carriers. The examples of FET are metal oxide semiconductor FET, that is MOSFETs, junction FETs, that is JFET, metal semiconductor FET, that is MESFETs, and heterostructure FET, very commonly known as HFETs. FETs are used in enormous applications, the applications being amplifiers, switches, current limiters, voltage controllers, resistors, mixers and oscillators. Different kind of FETs are represented in different ways. The JFET, MOSFET, MESFET, enhanced FET, they all have different representation. The figure shows the different representation which is very similar to BJT in some way for different kind of FETs. Metal oxide semiconductor FETs, that is MOSFETs, is actually a four-terminal device with four terminals being the source, represented as S, gate, the G, drain, D, and the body, P terminals. However, the body or the substrate of the MOSFET is often connected to the source terminal. Hence, this device can also be viewed as a three-terminal device. The advantages of MOSFETs are it is quite small in size, it operates at low power and very easy to fabricate. Hence, MOSFETs are very widely used for industrial applications. MOSFETs can again be of two types, the NMOS and the PMOS. NMOS is nothing but the N-channel device, whereas PMOS is a P-channel device. The difference between the representation of NMOS and PMOS is PMOS devices are represented as the bubbled MOS, as it can be seen in the figure. The charge carriers for NMOS are the electrons. The electrons enter and exit the channel at N plus source and the drain contacts, whereas the charge carriers for the P-channel device, that is the PMOS, are the holes. In this, the electrons enter and exit the channel at the P plus contact. The functionality of NMOS, a typical NMOS has the structure which is shown in the figure. It has the N plus source and a drain, a P plus substrate and the N plus gate. The potential barriers between the N plus source and the P type substrate can be modulated by applying a gate source voltage, that is VGS. So for actual working of the NMOS, when the VGS, that is gate to source voltage, is greater than the threshold, electrons get attracted and they start passing into the channel between the source and the drain. Thus, the MOSFET conduct current between the source and drain. This is the basis of the N channel between the source and drain. When the channel has a mobile electrons, we often call the channel inverted or describe it as having as inversion layer, whereas the case is different for the PMOS. In PMOS, to create an inversion layer in the N-type substrate, holes are attracted to the gate electrode. The P-type channel is induced, connecting the P plus well at the drain and the source. Thus, the PMOS device, we define current flowing from source to drain as positive current. So now we proceed with the IV characteristic of the MOS transistor. As it can be seen in the figure on the left hand side, the three different regions in the MOS are the pinch-off or the cutoff region, the active region and the saturation region. These regions are very similar to that discussed for the BJT module. Whenever the curves for the IDS versus the VDS are almost linear, this region is called as active region. Wherever the VDS is below the threshold, we call it that the device is almost into the pinch-off region. But if it goes on increasing, as the voltage goes on increasing and there is not much increase in the current, we call that the device has almost reached into the saturation region. These characteristics are also very clear with the IDS versus the VGS curve, which is on the right hand side. Different regions can be shown in it as well. That is, if the voltage, that is VGS, is below the threshold where the graph is almost constant, it is the pinch-off region. Whenever the curve starts becoming linear, it enters into the active region, and later it gets into the device, moves into the saturation region. So these are different characteristics for which the MOSFET functioning in three regions can be shown. So the modes of operation of the MOSFET are nothing but the cutoff region, the active or the triode region, and the saturation region. That is, as discussed, when the VGS is below the threshold, the device is in cutoff region. When the VGS is greater than the threshold and VDS is less than the VGS minus VTH in terminology, the device is in the active region. And if the VGS exceeds the threshold and the VDS exceeds the VGS minus VTH, device gets into the saturation region. Thank you.